So now we're ready to move on to the next big theorem called the Lebesgue decomposition theorem. This is a very useful theorem in probability, and I'll talk about why in the next video. So first of all, the idea is that suppose you're given two sigma finite measures. Here, let's assume they're just positive measures. We're not talking about sign measures. And we saw there are two notions. One is absolutely continuous with respect to the other. And there's another notion that's basically saying they're mutually singular, basically means they're supported on different sets. Okay, so you can decompose the entire set X into two null sets for both of them. Okay. All right, so the Lebesgue decomposition is basically saying the following. Suppose you are given these two sigma finite measures, that's called a nu and mu, then you can always decompose one of them into a absolutely continuous part. That's called the nu of A, that's the absolutely continuous part. And you can decompose it. The second part is a singular part, mutually singular respect to mu. Okay, so you can always find such a decomposition. And in fact, this decomposition is unique. All right, so I'm going to prove the decomposition part first, and then I'll leave the uniqueness and the application in the next video. Okay, so let's try to prove there exists such a decomposition. Okay. So the proof is there's a one standard trick when you are dealing with two sigma finite measures, even though they may not be absolutely continuous with respect to each other, you can construct one. Let's call it lambda to be their sum. Okay, just lambda to be mu plus nu. Okay, that's going to be a positive measure. And it's a quite standard trick to see that the mu and nu, they're both absolutely continuous with respect to lambda. Okay. So this is observation. So it's fairly simple to see why, because if you have lambda v is equal to 0, well, lambda e by definition is just mu of e plus mu of e, and the right-hand side, each one of them is going to be greater than or equal to 0, and two non-negative numbers, if they sum up to 0, then they both have to equal to 0, so this shows the absolute continuity. So now you have mu and nu both absolutely continuous with respect to this new measure lambda, so I can find a Radon-Nikodym derivative because everything is sigma finite. That's by our assumption. Okay, so by Radon-Nikodym, okay, so there exists a, let's call it a function f, where let's just use the notation f is basically d of mu divided by d of lambda. Okay, that's the Radon-Nikodym derivative of mu respect to the lambda. Okay. So the idea is the following. In fact, you can also actually just do the other one. So you can say was d nu over d lambda, and it's fairly simple to see this f plus g is going to actually be equals to 1 almost everywhere. Okay, because when you sum it up, it's basically d lambda over d lambda, which is equal to 1. Okay, but anyway, we don't need that much. The idea is I now want to decompose this new measure into a singular part. Okay, so what singular is basically means is basically only takes value when the mu is not taking any value. Okay, so it looks like as if when mu is equal to 0, that's where mu of s is going to be supported on. Okay, and the other one I want to make something absolutely continuous. Okay. So based on this kind of intuition, so let's consider the set where the nu takes the value 0, so that's kind of where the Radon-Nikodym derivative is taking 0. Okay, so so this is all the x where the f of x is actually equals to 0. And by the way, because mu and lambda are both positive measures, so it's clearly this f has to be non-negative, at least non-negative almost everywhere. So let's just assume it's non-negative. All right, so the set A is where the f is taking 0 value. Another way of thinking is on the set A, the lambda measure is solely based on the mu value, the nu value. Okay, the mu is contributing nothing. The f is 0 on the set A. So the lambda is really just taking the nu part. Okay, so ideally, I want to say that's going to be where the singular measure is supported on. Okay, so let's define the singular measure, so mu of s, to be nu restrict to the set A, and I define the restriction on the assignment, but let's just, for completeness, let's just say nu of S of E is essentially just nu of E intersect A. Okay, so I'm restricting myself on the set A. Okay, I want to show that's the singular part or mutually singular part to mu. And the rest of them are basically, let's call it B. So B is just the A complement. So that's whenever the f of x is going to be strictly greater than 0. Okay. So intuitively, that's basically saying that's the part where the lambda measure have some contribution from mu. Okay. It may have some contribution from nu as well, but we don't care. Okay. So let's define the absolutely continuous part, the nu of A part, to be nu restrict to this set B. Okay, so in other words, nu of A of, if you want to measure E, that's just nu of E intersect B. Okay, that's just by definition. And one thing for sure is that based on this definition, the nu of E, because A and B, they're just one is the complement of the other, so this is going to be nu of E intersect A plus nu of E intersect B. So this is indeed the sum of the first one is nu of S of E, and the second one is nu of A of E. Okay, so indeed we have nu is decomposed as the sum of these two measures. Okay, so at least this is true. So now I need to show two things. So first of all, I want to claim that the nu of S is actually going to be mutually singular to the mu measure. Okay, so I want to show these two are mutually singular. And just recall, basically, I need to find some f where basically nu of S restrict to this f is going to be 0, and mu restrict to the complement is going to be 0. Okay, that's what the mutually singular means. We define it for sign measure, but here it's just two positive measures, so it's basically the same definition. All right, so why is that? Well, we know one thing. Well, we know mu of B, okay, by definition, that's just going to be the integral of, sorry, I should say mu of A. The mu of A is just by the Radon-Nikodym derivative, that's the integral of the d mu over d lambda of d lambda, which by definition is just S, okay? So this is the integral of A of f of x d lambda. And if you recall our definition of A, we define the A to be where f of x is going to be equal to 0. So on the set A, the f of x is always equal to 0. So this is just no other than integral of 0 d lambda. Okay, so because f of x equals to 0 on x in A, okay, so you're integrating a 0 function, and that just equals to 0. Okay, so mu of this A is going to be equal to 0. Well, of course, so the nu restrict to this A is going to be 0. And I want to show the nu S, well, being mutually singular, just need to show it's going to be equal to 0 on A complement. Well, that's really easy. By definition, the nu of S, by definition, is just, well, nu of S of E is nu of the set intersect with A. So here we have A. I shouldn't have an S here, so it's the nu measure restricted to A. So it's the A complement intersect A. But that's just the empty set, which is mu of empty, which is equal to 0. Okay, so the nu of S and nu of S and mu, they're supported on different sets. Okay, so one is on A complement, one is on A, so they're mutually singular. Okay. So the second part, I need to show the following. I need to show the absolute continuous part is indeed absolutely continuous with respect to the mu measure. Okay, so I want to show that. So let's assume we have some set, let's say E, we have mu of E is equal to 0. Okay, suppose we have that. Well, what does that mean? Well, that just means the integral on E of this Radon-Nikodym derivative, I call it F, of this d lambda, that's going to be equal to 0. Okay. And if you recall how I defined this E, okay, well, if you can, we can break this E into where F is 0 and where F is non-zero, okay? So on the set A, so if I say E intersect A, I know the F is just equal to 0, okay? So on here, the f of x is actually equal to 0. And I can break it into the second part where E intersects B of f d lambda. Okay, that part is when f of x is actually strictly greater than 0. Okay, so I can break it into two parts. The first part, there's nothing much to say because f of x is equal to 0 on the set. Okay, you're integrating a 0 function, so that's going to be equal to 0. Okay, so the whole thing is just the integral. I only need to care where f is non-zero. So let's do the E intersect B of f d lambda. So right now we have a situation where we're integrating something that's strictly non-zero, well, but it still integrate to 0. Okay, the integral is still equal to 0. I want to make a claim that just implies the only chance this can happen is the E intersect B is just a null set. Okay, so I want to make, let's just make a following claim. So suppose I have some function, say, let's use a different function, g of x, is strictly greater than 0 on some set f, okay? And if I have the integral over this f of this g d lambda, if that's going to be equal to 0, okay, then I want to claim that lambda of f is equal to 0, okay? So the only chance you can make this happen is you're integrating over a null set, okay? So the proof is, well, it's not too hard, okay? So for each n, so you consider, because g of x is greater than 0, so it has to be greater than 1 of the 1 over n, so you consider all the x where g of x is greater than 1 over n, okay? Well, that's going to be contained in f, okay? And this set cannot have a non-zero measure, okay? Because if it has a non-zero measure, then you just define 1 over n times the characteristic function, and it's a simple function smaller than or equal to g, so, well, that will contradict the integral being equal to 0, okay? So you can convince yourself the lambda measure of the set where g of x is greater than 1 over n, okay? That's going to be equal to 0, okay? If it's non-zero, then we will have a contradiction. There's no way the integral is 0. And you just let n to be any n, okay? So you take their union. So you take union n greater than or equal to 1 of all these sets where g of x is strictly greater than 1 over n. Well, that's still going to be 0. That's just by the sigma subadditivity. And, well, this union is essentially where g of x is strictly greater than 0. Okay, so we should make the x is inside f. Okay, so here's x inside f. So g of x is greater than 0 on all f, so this union is going to be equals to f. Okay, so that will tell me the lambda f is equal to 0. Okay, so as expected. So now let's go back. So we can apply this claim to the situation here. I have an integral of a strictly positive function on E intersect B, because f is strictly positive on E intersect B. The only chance this can happen is that, so by the claim, the only chance is that I'm integrating over a null set. Okay, so the E intersect B, that has to equal to 0. Okay. And because that's going to be equals to 0, okay, so, and I have the nu of is absolutely continuous with respect to lambda, okay, because lambda is the sum of these two. So automatically I have the nu of this E intersect B is also equal to 0. Well, but what is nu of E intersect B? Well, by definition, that's just how we define nu of A, the absolutely continuous part. We say nu of A is the nu restrict to this B. So by definition, I got nu of A equals to E. Well, so if we look back what we did, we start with a set E where mu of E is equal to 0. That's where we start. And now we obtain the mu A of E is also equal to 0. Okay. So basically that just shows the nu A is absolutely continuous with respect to mu. Okay. So now we proved there exists one such decomposition as the absolutely continuous part mu of A and the mutually single part mu of S. So in the next video, we're going to show this decomposition is in fact unique.